There are inventions so small they can fit in the palm of your hand, yet powerful enough to change everything. Superglue is one of them, a material capable of bonding in seconds what once seemed impossible to repair. Whether it's wood, metal, or ceramic, just a single drop can achieve what other tools cannot. But how does it manage such strength in so little time? To find out, we head to China to explore the production process. Adhesives have deep roots. Thousands of years ago, prehistoric humans used tree resins such as birch, heated to create tar that bound stone tips to wooden handles for hunting tools. In ancient civilizations, Egyptians mixed gum arabic for papyrus and bone glues for furniture, while Romans and Chinese relied on blood or rice starch for mosaics and scrolls. These natural adhesives were clever but slow, sensitive to moisture, and insufficient for an industrialized world. The breakthrough came in the 20th century. In 1942, during World War II, Harry Coover at Eastman Kodak experimented with cyanoacrylates for transparent plastics, but dismissed them as being far too sticky. In 1951, a laboratory accident, bonding prisms of a refractometer, revealed their adhesive potential. Coover refined the formula, and in 1958, Kodak launched Eastman 910, the first commercial superglue, strong enough to hold tons with a single drop. Since then, its production has been perfected in high-technology plants. So how exactly is superglue made? It all begins long before the machines are turned on, with the selection of raw materials at the core of the process. The central ingredient is ethyl cyanoacetate, an organic compound not found naturally, but produced in chemical laboratories from acetic acid, the same acid that gives vinegar its flavour, and ethyl alcohol, the common alcohol found in spirits. This compound is combined with cyanide inside specialized reactors under tightly controlled conditions, creating the substance ready for industrial use. This material arrives at the plant in hermetically sealed drums, along with another key chemical, formaldehyde. Although it appears as a colorless gas, it requires extreme care because it can be irritating. To handle it safely, it is stored in large, pressurized stainless steel tanks designed to prevent leaks or escapes. Why such strict attention to purity? Because even a microscopic impurity, measured in parts per million, can completely disrupt the process. It's like a perfectly prepared soup ruined by a single spoiled ingredient. The same principle applies here, but on a chemical level, where the consequence can be uncontrolled polymerization. To protect the materials, inert gases such as nitrogen or argon are used. Their role is simple but critical, filling empty spaces in tanks and reactors, displacing oxygen and moisture that could destabilize the mixture. It's the same principle used in potato chip bags filled with nitrogen, not by chance, but to keep them fresh and crisp. Here, that protective blanket keeps the chemicals stable until needed. Chemical inhibitors also come into play, such as hydroquinone, phosphoric acid, or sulfonic acids. These act as brakes, tiny barriers that prevent reactions from triggering too soon. Alongside them, other additives have more specific roles. Fumed silica helps thicken the mixture. Synthetic rubber adds elasticity and flexibility. And colorants allow manufacturers to adjust the appearance in commercial versions. Nothing enters production without first passing strict controls. Each batch of raw material is analyzed in the factory's laboratories using high-precision techniques. Infrared spectroscopy confirms that the molecular structure is correct. Gas chromatography identifies even the smallest impurities, and pH tests ensure that the chemical environment remains slightly acidic, a condition that grants the product greater stability. The rule is simple: if a drum fails these tests, it never enters production. Even the slightest trace of water or an unexpected variation is enough to send it back to the supplier. The reason is clear. In such a delicate system, a single mistake can collapse the entire process, much like a house of cards. With the raw materials verified and approved in the laboratory, the first major chemical stage begins: the Knovenagel condensation reaction. This step is like opening the main door to the production process, because from here, the foundation is built for everything that follows. The scene takes place inside an industrial reactor, a massive tank made of special glass or coated stainless steel, both materials chosen for their resistance to corrosion. It is no ordinary vessel. It is equipped with internal agitators that spin like ship propellers, ensuring the mixture remains uniform from start to finish. Imagine a giant cauldron, not for soup, but for a precise combination of ethyl cyanoacrylates and formaldehyde, dosed drop by pumps that measure every milliliter with perfect accuracy. The reaction does not begin on its own. It is triggered by heating the mixture to temperatures between 100 and 120 degrees Celsius under controlled pressure. At this point, the system releases exothermic heat, energy produced as a result of the reaction. To picture it, think of mixing baking soda with vinegar. The reaction releases bubbles and energy, except here the process is far more complex and on a much larger scale. Temperature control is an absolute priority. If the heat rises too far, the compounds could decompose or even trigger a violent reaction, similar to a pressure cooker without a safety valve. To prevent this, the reactor is surrounded by cooling coils where cold water circulates, keeping the temperature stable at all times. Meanwhile, a digital sensor system continuously measures pressure, temperature, and pH, sending data to software that records it second by second. The result of this first reaction is an intermediate polymer, a thick liquid with the texture of honey. Along the way, a byproduct is also generated, water. And here lies another critical detail, that water must be extracted with precision, because leaving it in the reactor would be like leaving a drop of yeast in dough. It would eventually trigger an unwanted transformation. To remove it, vacuum distillation is used, a method that evaporates water by applying suction instead of excessive heat. It's like squeezing out the very last drop of juice from an orange, but without damaging the main pulp. Once the water has been removed, operators fine-tune the parameters by adding small amounts of weak acid to keep the pH levels low, which slows down any attempt at premature polymerization. At the same time, fine mesh filters with microscopic pores remove solid impurities that could affect the quality of the final product. If water were to remain in the mixture by mistake, the polymer could harden inside the reactor, forming a solid block that would not only ruin the batch, but also force the plant to shut down for days while everything was cleaned and restarted. This is why every minute of this step requires constant monitoring and precise adjustments. The reaction time varies between 4 and 8 hours per batch, depending on the size of the reactor. In large-scale facilities, equipment can reach capacities of up to 10,000 litres, capable of producing several tons of intermediate polymer in a single day. The next major step is thermal cracking, the stage where the thick polymer obtained earlier is broken down into the reactive monomers that will make superglue possible. In other words, this is where the substance is split into smaller building blocks, ready to become the ultra-fast adhesive we know. To achieve this, the viscous liquid is transferred to a secondary kettle, a tank specially designed to function like an industrial oven with a precision thermostat. Inside, the product is heated to about 200 degrees Celsius by internal coils that distribute heat evenly. The heat acts like invisible scissors, breaking the long polymer chains into smaller fragments and generating volatile monomers of ethyl cyanoacrylate. Once released, these monomers evaporate and rise through pipes, similar to steam escaping from a kettle, except here, instead of water, it is a highly reactive chemical. To capture them, the vapor passes through refrigerated condensers, where it quickly cools and transforms into a transparent liquid collected in stainless steel tanks. Purity is essential at this stage, so the liquid is not considered finished yet. It undergoes multiple distillations in fractionating columns, which separate the components according to their boiling points. The process is much like passing grains through sieves of different sizes, where each level removes what does not belong. With every distillation, traces of uncracked polymers, impurities, or byproducts are eliminated. The goal is to achieve a purity higher than 99.9%, because even the slightest impurity could cause the glue to cure more slowly, lose strength, or produce unreliable bonds. To optimize the process, catalysts, usually organic acids, are used to make chain breaking easier without needing to raise the temperature too high, reducing energy consumption. The residues that fail to evaporate are not discarded. Instead, they are collected and recycled for another cracking cycle. an important detail in an industry that strives to minimize waste whenever possible. Throughout the procedure, a constant flow of nitrogen is maintained. This inert gas pushes out moisture and oxygen that could trigger unwanted reactions. At the same time, pressure sensors ensure there are no leaks, since any air intrusion would compromise system stability. Thus, a thick syrup is transformed into a crystal clear liquid, ready to become the heart of the adhesive. With the monomers obtained, the stabilization stage begins, arguably the most delicate part of the entire process. These monomers are so sensitive that a single breath of humid air is enough to trigger immediate polymerization. If left unchecked, the glue would harden before ever reaching the consumer. To prevent this, chemical inhibitors are added in microscopic quantities, measured in parts per million. Hydroquinone neutralizes free radicals, while acids such as phosphoric or sulfonic keep the environment acidic, blocking the action of basic ions that could start the reaction. The method is comparable to seasoning a giant stew. Just a pinch at the exact moment makes all the difference. The mixture is stirred with slow-moving paddles, enough to homogenize, but without creating turbulence that would introduce air. It then passes through nanometer membrane filters, so fine they can trap particles the size of invisible grains of dust. Quality control at this stage is intense. Mass spectrometry is used to confirm no contaminants remain, and reactivity tests ensure the monomer does not cure inside the container, but will cure instantly when applied to a surface. This is also where the product is customized according to its final use. For medical applications, octyl cyanoacrylate is manufactured, synthesized from octanol instead of ethanol. Its longer chain degrades more slowly in the body, releasing less formaldehyde, making it suitable for sealing surgical wounds. For industry, methyl cyanoacrylate provides ultra-fast curing on metals, while butyl cyanoacrylate is preferred for plastics thanks to its elasticity, which prevents fractures in flexible materials. Each formula is tested under standard conditions. Small drops are placed on glass, steel, or synthetic skin, and the exact curing time is measured with precision stopwatches. This guarantees compliance with clear specifications, for example, 5 seconds to bond metals and about 10 seconds for porous plastics. The stage of additive incorporation is the moment when superglue stops being just a stabilized monomer and becomes a tailored product designed to meet different needs. Here is where chemistry becomes versatile, almost custom-made. The stabilized monomers are transferred to secondary mixing tanks, always under a nitrogen atmosphere that displaces any moisture. In this controlled environment, the modifiers are added. One of the first is fumed silica, a powder so fine it is lighter and subtler than talcum. It is dispersed using high shear agitators, spinning at speeds close to 10,000 revolutions per minute, like industrial blenders capable of breaking down any clump. The result is a thick gel that does not drip, ideal for applications on vertical surfaces or for filling gaps, something a pure liquid could not achieve. This practical detail makes it possible, for example, to repair cracked ceramics or splintered wood without the adhesive sliding out of place. Another key additive is synthetic rubber, such as polyisobutene. This material is blended in to improve impact resistance, preventing the bond from shattering like glass under stress. In industrial applications, accelerators such as ammonium salts or amines are added. These allow the adhesive to cure at very high speed, highly valued in assembly lines where every second matters. Colorants are sometimes included as well, occasionally fluorescent or bluish, helping operators clearly see where the drop is applied, especially in precision work. For premium versions, special inhibitors like calixarenes are integrated to extend shelf life, ensuring the product does not lose its properties over time. Each additive is measured on precision scales because even the slightest excess or shortage can alter the adhesive's properties. The mixture then passes through homogenizers that act like giant beaters, dispersing everything uniformly with no clumps or texture variations. At this stage, controls include rheological analysis, which measures how the adhesive flows under different conditions, and strength tests performed with dynamometers capable of applying stresses up to 25 megapascals. To put that in perspective, This force is equivalent to holding up a small car with nothing but a properly made adhesive bond. With the formulation complete, the packaging stage begins, a highly automated process that combines speed with accuracy. The mixture flows through inert polyethylene tubing, a material that does not react with the adhesive, into rotary filling machines. These machines work like precision carousels, able to dose anything from as little as 0.5 grams in tiny tubes to 50 grams in industrial bottles. In just minutes, hundreds of containers are filled with the same exactness. The container material, whether high-density polyethylene or polypropylene, is carefully chosen because its hydrophobic surfaces do not trigger polymerization. It works like a non-stick pan. Everything slides off, preventing the glue from hardening inside. Filling takes place in chambers where humidity is kept extremely low, using dry air or nitrogen to ensure that even the slightest trace of water vapor does not ruin the contents. Next, caps are screwed on with calibrated torque, and the container bottoms are sealed with thermal plates. Labels are laser printed, including warnings and recommendations such as "Do not use near eyes," "Do not apply on polyethylene or polypropylene plastics," and use acetone for removal. For medical products, the packaging undergoes sterilization with gamma radiation in sealed chambers, guaranteeing it reaches surgical environments free of microorganisms. The production line is equipped with optical sensors that detect defects such as misaligned caps or internal bubbles, automatically diverting faulty containers for recycling. In high-capacity plants, multiple parallel lines operate simultaneously, producing thousands of tubes per hour, all packed into boxes with QR codes that allow each batch to be traced from origin to final destination. After packaging comes quality control, the true guardian of the process. Here, tests resemble forensic analysis. Nothing is left to chance. Viscosity is measured with rotational viscometers that simulate adhesive flow under different conditions, ensuring the product is neither too thin nor too thick. Curing time is tested by applying drops on standard surfaces like glass, steel, or plastic, and the reaction is timed with millisecond precision, verifying that it falls within the expected range, 3 to 10 seconds, depending on the material. Bond strength is evaluated with dynamometers that apply traction or shear, reaching resistances of up to 30 megapascals. To visualize that, it is like lifting an elephant with nothing more than a 5 centimeter square of adhesive. Stability is also simulated under different climates, placing containers in chambers that replicate everything from tropical environments to cold storage warehouses. Other tests include gas chromatography to detect impurities and ultraviolet spectroscopy to confirm molecular composition. In medical adhesives, biocompatibility tests are also performed by exposing the material to cell cultures, verifying that it does not cause toxicity. If any batch shows deviations, such as a longer than expected curing time, it is isolated and analysed to correct the formulation. Meanwhile, worker safety is also monitored. Operators use masks with HEPA filters, nitrile gloves, and ventilation systems that capture formaldehyde vapours, neutralising them in chemical scrubbers. All this rigour has one clear objective: ensuring that every tube of superglue delivers exactly what it promises, whether repairing a vase at home, assembling electronic components, or even sealing tissue in surgery. Each package, in the end, is the result of science, control, and precision working together. And that is how superglue is made. Tell me, what did you think of this process? I'll read you in the comments. If you enjoyed the video, click the like button and don't forget to subscribe to the channel. In the windows you'll see next, there are more videos that might catch your interest. Go ahead and watch one. See you next time.